Hello, myself Aniket Zabde. In our project AI integration for improving sensor data quality in predictive maintenance, I contributed in project for data visualization and dashboard development.
Hello everyone, myself Vikas Tegi. My project name is AI Integration for Improving Sensor Data Quality in Predictive Maintenance. My contribution to the project is anomaly detection and feature scope.
Hello, myself Amitiki. My project name is AI Integration for Improving Sensor Data Quality and Predictive Maintenance, and my contribution to the project is AI Anomaly Detection and Predictive Maintenance.
Hello everyone, myself Rahul Gorpade. Our project topic is AI integration for improving sensor data quality in predictive maintenance. And my contribution to this project is overview of results and IBM cloud deployment.
Myself Niket Zabde. Our project is AI integration for improving sensor data quality in predictive maintenance. In that project, uh, introduction part is the predictive maintenance help for the equivalent failure. In that we having by analyzing the data in real-time sensing regarding the previous maintenance, identifying early signs for potential failures, allowing intermediation before the background occurs. And the second part is the sensor data quality is crucial for the accurate prediction. In that sensor is effective for the data, sensor must be accurate, reliable on consistent. It have maybe it have some poor quality data lead the incorrect prediction, resulting in repairing or misleading information. In the third part is AI techniques for improving reliability and accuracy. In this part, AI and the machine learning models can be process large data set from sensor, identifying complex patterns and the predictive failures with a high degree of accuracy. This technique is consistently learning for the new data, improving their predictive over time, and its overall system for reliability. The second part in our project is the project objectives. In that we have three objectives mainly used in the project. First objective is to improve the sensor data quality for predictive maintenance. In that we having the different objectives. First one is to be the missing in implementation. We have the different types and predictive maintenance. The second one is the handling misleading values and detection anomalies. In that we are in some condition we get the poor quality of the data. It may be affected to the detect the anomalies in present in the AI sensors. The third objective is use AI models for classification and trade analysis. The AI analysis is using the sensor. We get the trade and we collect that data for the our future and our future data collections. This is our mainly three project objectives. We having data processing for mainly three. In that we have missing value handling. Second one is outlier detection using the z-scores method. Noise reduction with the glory filters. In that the z-scores method is mainly used for the data pre-processing for the AI sensors for in different sectors. And third one is noise detection. It is also useful for the different fields. And our in project the features of engineering are mainly acquired in extract or ruling and standard deviation. Second one is capture trends and in sensor readings. Third one is preparing data for anomaly detection and modeling. These three features are important for the AI sensors.
Myself Vikas Tegi. The continuation part of this project is the anomaly detection. Used isolation forest to detect anomalies, and it also identifies unusual patterns in sensor data. It also helps in proactive maintenance and decision making. Next is predictive modeling. It is used in random forest classifier for fault prediction. And next, hyperparameter tuning with grid search CV. Model evaluated using accuracy, ROC, AUC and F1 score. Visualization. Visualization is used in interactive plots with Plotly for raw versus smooth data. Correlation heat maps using Seaborn. Anomaly visualization for better insights. What is visualization? Why is visualization important? Visualization is important because it is easy to interpretation. It converts complex. It con- Why visualization is important? It is important because it is easy to interpretation. It converts complex numerical data into very visual for quick insights, and it is also used in pattern recognition. It helps it helps to identify trends, anomalies, and correlation, and it is used in decision making, assist business and researchers in making data driven decisions. It is also used in communications, makes it easier to present findings to stakeholders. Future scope of this project are AI enhances sensor. Feature scope of this project are AI enhances sensor data quality for predictive maintenance. Future work, deep learning for better predictions, and also used in it has a best future scope in real-time anomaly detection system implementation.
Let's move on to the coding part. Myself Amit Tegi and my colleague Rahul Gorpade will discuss on to the coding part. Our code has splitted into 11 individual steps. I will be explaining the 5 individual steps. Okay, let's move on to the step 1. Data ingestion and data initial exploration. Data ingestion, it reads the sensor data from a CSV file and displays an overview of the dataset, including column names. It converts the timestamps column into a date time format if it exists. Otherwise, it creates a dummy timestamps. Okay, step 2. Step 2 is the data preparation and data cleaning. It handles the missing data, uses k nearest neighbors to fill the missing values based on the similar data points, and the removing of duplicates. Drops duplicates rows to prevent data bias. Outlier detection and removal. Applies the Z-score method to filter out extreme values. Noise reduction. Uses Scavity-Golay filter to smooth high frequency noise while preserving trends. Feature selection. Feature scaling. Apply standard scaler to normalize all features. Step 3. Data visualization for quality assessment. Raw sensor data plot. Plots the original sensor values over time. Smooth sensor data plot. Compares the raw sensor data with smoothed values. Correlation heat map. Uses Seaborn heat map to visualize feature correlation. Step 4. Anomaly detection. Implements isolation forests as unsupervised anomaly detection algorithm. It classifies anomalies and normal values, then maps 1 to anomaly and 0 to normal. Plots the detected anomalies in red. Feature engineering. It computes the rolling mean and rolling standard deviation over 5 time frame window.
Myself Rahul Gorpade. Let's see what is there in step 6. Predictive modeling for failure detection simulates the failure labels with 95% normal and 5% failure distribution. And it helps in extract sensor features like mean, standard deviation, median, and handles the missing values present in the data. And it helps to split the data into training 80% of the data and testing 20% of the data into sets. Uses the grid search CV to optimize random forest classifier. And let's see what is there in step 7. In step 7, we inserted the predictive failures using a trained model. Calculate accuracy using F1 score and ROC and AUC to access model performance. It helps to print evolution matrix for quick performance analysis, and it ensures a well-balanced model for predictive maintenance. And step 8. Fairness matrices evolution. In fairness matrix evolution, we stimulate the sensitive attributes for fair analysis and computes demographic parity difference to check bias in failure prediction. And demographic parity difference, also known as DPD, and calculates the equalized odds difference, which is also known as EOD, to evaluate equal treatment. Ensures the model does not favor one group over another. Step 9. Performance monitoring and reporting. Defines a baseline accuracy for model drift detection, compares current accuracy with previous performance, triggers warning if accuracy drops by more than 5%, suggests retraining, ensures the model stability over time for industrial applications present in the data. And in step 9, if the drops more than 5%, it suggests to retrain the model or the data present. Step 10. Additional visualization for in-depth analysis. Computes a sensor health metric using an inverse rolling standard deviation. Generates time series plot to monitor sensor health trends. Creates an interactive sensor data plot using Plotly. Visualize key patterns to understand sensor behavior. And using the visualization sensor behavior, we can predict. And finally, the step 11. In step 11, we can summarize the data pre-processing, handling the missing values like noise reduction, outliers, etc. etc. And in step 2, in step 11, second is report best model parameters and cross-validation results. Include fair matrices to ensure ethical AI, least generated visualization for raw data trends and health monitoring. And finally, this structure ensures a well-rounded, interpretable, and deployable predictive maintenance model could like any kind of the data can be predicted. Let's see the output of this. And this is the output for the data. We can see the raw center data distributed in a visualization in which y-axis states the sensor value and x-axis states the timestamp. So using the visualizations we can get a clear view of the data. And let's see the difference between the raw data and smooth data, in which blue color denotes the raw data and yellow dotted line denotes the smooth data. So we can have the sensor value and timestamp present. So this is the heat map of the heat map, or also known as correlation matrix of numeric parameters, in which we can see the rolling mean, rolling standard deviation, failure detection sensor and smoothed sensor. Okay. And let's see the last anomaly detection in sensor detection, where red color denotes the anomalies present in the data. So this is all the present. So let's see the terminal part of this. It is a correlation model, came from a model performance evolution classification reports, in which we can see the data, and the ROC AUC value is 0.5, F1 score is 0.0, and confusion matrix is also present. Let's see the comprehensive report summary. Data pre-processing. Missing variables handled via KNN imputation. Duplicates removed and outliers filtered using Z-score method. Noise reduction applied using filter. Feature generation. Rolling mean and rolling standard deviations features added. In 3. Anomaly detection. Isolation forest detected 747 anomalies in the data. Model training. Best random forest parameters. Max depth none, mean sample split into 2, and n estimators are 50. Mean CV F1 score is 0. As we discussed earlier. Model evolution, accuracy is 0.97, F1 score is 0.0, ROC AOC value is 0.50, and fairness matrices, geographic parity differences 0.0, and equalized odd differences is 0.0. Visualization generated for the raw data, smooth data, correlation, sensor health, and interactive exploration. And all the needs basic necessities we uploaded in our the GitHub channel. Thank you.